This video is about parametric modeling and how to use the TI calculator in order to use parametric mode. So parametric equations are often used to simulate motion. And 3 out of the 4 problems on this worksheet don't really use X and Y for motion, but we can still at least get the idea before we get into some other problems later that involve both X and Y more often. Using parametric equations, we can specify not only where the object travels, but how quickly it moves, and that's something that we can use with regard to the parameter t. Graphing calculators can simulate this situation in parametric mode. You'll also want to change the graphing mode to simultaneous, and what simultaneous does is it graphs all of your lines or curves at the same time, whereas in sequential mode, where it normally is, they graph one at a time with y1, y2, y3. Well, in this case, it's going to graph your x1 of t, y1 of t at the same time as your x2 of t, y2 of t. And then you can also change the style from a line into a circle. That's over here, so you can watch the movements. T-step is another thing that we need to be aware of. So T-step is something that shows up when you go to the window, and that dictates how many ordered pairs are created. It substitutes in a value of t every t-step. So for example, if you're starting at t equals 0, and your t-step is 0.1, that means it's going to start at 0 and then plug in 0.1, 0.2, 0.3, 0.4, 0.5, all the way until your t end, all the way until your final t value. So you have a t start, a t end, and a t step. A larger t step allows the graph to be completed faster, but the trade-off is a sacrifice of accuracy. So the smaller the t-step, the more points they create, which means there will be a more accurate graph. Now, on a lot of things that we do on this worksheet, it's not ultra important because they're lines. But once you start getting into curves and parabolas and things, then if you have really large t-steps, then you're going to end up with things that don't actually look like curves. They're going to look like a bunch of straight lines connected together if your t-step is too big. And then you don't have a very accurate picture. Here's example 1. This does not actually need a calculator, and neither does example 2. Both of these are pretty straightforward lines. But Ben can sprint at a rate of 24 feet per second. Jerry goes at 20 feet per second. And Ben gives Jerry a 10-foot head start. So what we see is we have Ben with 24 feet per second times t seconds, and Jerry with 20 feet per second times t seconds plus the 10-foot head start. Now the deal with y is you can kind of pick whatever y you want because it's not that important in this problem. They're really only going in one dimension. But I chose 2 numbers that aren't the same, so then you can clearly see them separately, and you're not looking at 2 lines that are overlapping, because if you pick the exact same line for y, then they're going to end up overlapping each other. Now, how did I find where the t's are done? I just set 24t and 20t plus 10 both equal to 300 because that's when they finished the race. Now, when I graphed it on the TI, I just made my Tmax 15 because it doesn't really matter that much. Once they cross the end of my screen, then I know that they've finished the race because I made Xmax equal to 300. And then my y, it can be anything I want. It just has to include the 2 y values that I chose. So who's ahead after 3 seconds? We just substitute 3 into the equations, and you see that Ben's ahead by 2 feet. And who wins the race? Well, the answer is Ben by 2 seconds, but we can actually figure that out by substituting 300 in for x in both of these equations. So 300 equals 24t. dividing by 24, and you see that 12.5 is when Ben is done. So he's done at 12.5 seconds. If I set 20t plus 10 equal to 300, I see that Jerry finishes at 14.5 seconds. So Ben would win by 2 seconds. Again, none of this really needed a calculator, but we can see how it looks on the calculator to at least figure out what's going on. Now, Tanya, as a distance runner, runs at an average velocity of 8 miles an hour. 2 hours after Tanya leaves your house, you leave in your car and follow the same route. If your average velocity is 40 miles an hour, how long will it take you to catch up to her? So Tanya's equations are 8t and then any value of y that's going to fit on your screen, because again, this is really a one-dimensional problem. The car is 40 miles an hour times t minus 2. And the reason why you have a t minus 2 is that you are starting 2 hours after Tanya begins. So if we graph this situation, we want to go to t equals 2.5. And the reason why we want to do that is because if you set these two things equal to each other, you see that the catching up would occur at 2.5 hours, which again indicates that I don't really need a graphing calculator to answer this question. This question is pretty straightforward. And again, like I said, the y's, it's not really important what you pick. You could even have them overlapping, but you probably don't want the car to run into Tanya. That's not very nice. But I have them separate just so it's easier to see them and they're not going to overlap each other. But you could put them at the same y value if you wanted. When an object is propelled upward with some sort of angle to the horizontal with an initial speed v0, then the resulting motion is called projectile motion. Gravity pulls down on it. And so there's the acceleration due to gravity in the y equation. So the x equation is kind of dictating how far the object is going to travel before hitting the ground, essentially. And that goes at a constant speed, assuming that wind is going to stay the same and stuff. And then the y component is going to have gravity pulling down on it. So that has a parabolic motion to it. So it's negative 1/2 gt squared plus v0 sine theta t plus h0, where h0 represents the initial height. So x is the initial velocity times the cosine component. And the reason why we have a cosine and a sine component is if the object is propelled at some sort of velocity with some sort of angle, then the amount that it goes in the x direction, the amount that it goes in the y direction at the beginning, v0 sine theta and v0 cosine theta. So that's how much happens at the beginning. And then obviously the y component has gravity pulling down on it, whereas the x component doesn't. So that's why this doesn't change at all. It doesn't have this 1/2 gt squared involved. So let's simulate the motion of a ball thrown straight up. So that's a 90-degree angle, which means, again, we have one component of these two that is irrelevant. You basically could have put it wherever you wanted. But the x component is not changing in this problem. Then there's the initial speed of 100 feet per second from a height of 5 feet above the ground. So I just plug everything into the formula. I end up with negative 16t squared plus 100t plus 5. And if I want to find out where it hits the ground, I just use the Pythagorean theorem on this thing because it's unlikely to factor. So I do that and I end up with 6.2996 or 6.300 basically. It's where that's going to hit the ground. So that is the set of parametric equations that models that. Then number 4, we have this White Sox behind with the bases loaded in the 9th inning. Luis Robert hits the ball 3 feet above the ground, angle of 20 degrees, and the ball leaves with an initial velocity of 100 feet per second. He hits it straight towards center field, and it's a 400-foot fence, 11.5 feet off the ground. So I just plug everything into the formulas again. I have 150 cosine 20 is my initial x velocity times the time. Then I have negative 16t squared plus 150 sine 20 degrees t plus 3 is my y component of the point where the ball is. If I want to know where the ball is going to hit the ground, I can see that by, again, doing the Pythagorean theorem on this, or not the Pythagorean theorem, the quadratic formula on this thing. If I said Pythagorean theorem up here, I greatly apologize. That's the quadratic formula, and you would think that a math teacher would know that. So we have the quadratic formula, and we would probably just either do that, or we can type this in calculator and just see where it intersects the axis using regular rectangular mode. You can do that too, or use polysymult or some sort of graphical utility to be able to find the intersection of that with the x-axis. So then we see if that actually intersects with the fence. And so we can draw a fence on our graph, on our TI, by using the line feature. So we graph line 400, 11.5, 400, 0. So essentially what that does is it just graphs a line segment using these 2 points. Then we press enter and we see that the graph shows up and the White Sox do win. The ball goes over the fence. Now, we can do this by hand also. Now, when I say by hand, I'm putting hands in quotation marks because we don't really want to do this by hand. We're going to have to use a calculator. But what we would do is we would take the y component of this and set it equal to 11.5. So what that will do is it will tell us the time at which the ball is at the fence. And there's 2 t values, but one of those t values is right at the beginning of the problem, and it doesn't make any sense. So we only want the one that's near the fence, and that would be 3.031. Then you would sub that t value into your x, and if you sub that into your x parametric equation, you'll find out how far the ball is. So if the ball is less than 400, the White Sox don't hit a home run. And if it's greater than 400, they do hit a home run. And we see if it gives x greater than 400. It does give us that at 427.231 feet. So the answer is yes. Now, suppose just as the ball's hit, there's a 12-foot per second wind blowing in from center field. Then we would change the 150s to 138s. So we have these equations now. And I'm not going to graph that with a live video version, but I just graphed it here, and you can see that it clearly goes short of the fence. So you can graph that on your own and kind of see it, or you can solve it using the exact same method that I did here to confirm that this x value is going to end up being less than 400, which means it's not a home run.